Let's introduce the concept of unit vector. They are very, very, very important and will be the only one you can rely on as you move on to dimensions higher 2. So let's consider a position vector for now. Let's consider a coordinate system, positive x, positive y, and 2 points. Let's say point C, -2 and 1, and point D, -4 and 6. Let's imagine 2 is here and D is here. We know about position vector, therefore we know that the position vector CD starts at C and ends at D. Therefore, this is the vector CD. And we know how to calculate it. We take the final minus the initial. So change of x and change of y. So the change of x would be the xd minus xc, which is -4 minus -2. That is -4 plus 2, or -2. And the y would be 6 minus 1, which is 5. Let's double check. Sure, that's good. X negative, y is positive. That means this vector is going in the second quadrant. Good. Now we know that the unit vector by convention that are aligned along our axis are called I for I, J for Y, and K for Z, if we add a third dimension towards us. And we know that those have to have little hats on top of it to differentiate them from regular vectors, which can have any magnitude. The ones with the hat have to have a magnitude of 1. It's gotta be a vector, a unit vector, along the direction of the position vector CD who has units of 1. CD may have a different magnitude. We can calculate it. CD magnitude is nothing else but -2 squared plus 5 squared, and we take the square root. So roughly square of 30, so obviously bigger than 1. It's gotta be a unit vector that starts at C and has a length of 1. Let's call it ECD. Any position vector can be associated with its own unit vector. And remember, vector can be moved around. So it can start at D, it doesn't matter. Or it can be moved to the origin, it doesn't matter. The point is, this has to be possible for us to calculate the unit vector of any regular vectors. How are we going to do this? Well, it's actually not too bad. Remember when we first introduced the concept of vectors? Let's consider the easy vector A that goes like this. 2 units. Obviously, A is equal to 2 times I. We run twice the unit vector I, and since I is along the x direction, we know I is horizontal to us. This is what we call the unit vector notation, because it is expressed in terms of its magnitude and direction. But the nice thing about the unit vector notation is it's separated. When we write a unit vector in Coco notation, we have to extract the magnitude like this, and we have to extract the direction by taking the arctangent of 5 divided by -2, the usual method. So we have 2 extra steps to do. Those 2 pieces of information, such as the magnitude and the direction, is somewhere hidden in there. But it's not very clear. We have to do 2 more steps using a trick to extract it. The advantage of the unit vector notation is that those 2 are nicely expressed and separated. In this case, this is obviously the magnitude of A, and this represents its direction. Magnitude and direction. So we've managed to separate the 2. Okay? So in general, we can do that for any vector. But before we do this, let's just solve for I. I is nothing else but A divided by 2. What is 2? 2 is the magnitude of A. Therefore, we can write I as vector A divided by its own magnitude. This is how we define and calculate a unit vector. So, for us, if we want to calculate ECD, and we know that any unit vector can be calculated by taking a vector divided by its own magnitude, then we can write that ECD if this is unit vector of position vector CD, it is equal to the vector CD divided by its own magnitude. Does it? That's simple. Because we also know that vector CD is n times that unit vector. In this particular case, this much. So, position vector CD is trivial. We've done it here. Negative 2i plus 5j. And then we're going to divide it by its own magnitude, which is square root of 30. Or 29 to be exact. Hence, ECD is negative 2 divided by square root of 29 in the I direction, and plus 5 divided by square root of 29 in the j direction. That's our unit vector, as being expressed in component notation. Okay? So now we can express position vector CD as its own magnitude, CD, times its unit vector. Hence, it would be square root of 29 times unit vector ECD, negative 2, 29, plus 5, square root of 29. Obviously, as you apply now the distributor rule with scalars, the square root of 29 is being distributed to both terms, and you end up with your original vector. So, it works. You can also double check that if you calculate the magnitude of this, you're going to get 1. Minus 2 squared is 4. Square root of 29 is positive 29. And we're going to add the square root of the j component, which is 25, 5 squared, divided by the square root of the square of the square root of 29, which is 29. And sure enough, 25 plus 4 is 29, divided by 29 is 1. It has to be 1. Okay? So in 2D, you may think, well, who cares? And you're right, 2D, not so useful. 3D, very useful. And it's also very, very useful if you like to relate vectors. For example, if you have a bar that are attached by 2 points, A and B, and you like to figure out the force along that bar, we call this an axial force, because compared to a shear force, which will be perpendicular. So if looking for the axial force, the internal force along the bar AB, then we know that this force is along the bar. Let's call it F. It might be going that way, or it might be going in the opposite direction. That means it could be a tension or a compression on the bar. But at least we know it's in this direction. Now, all we have to do is figure out the magnitude. If you actually have that bar, well, you can take measurements. You can pick a coordinate system, 2D, 3D, doesn't matter, and you can measure the coordinate of A and the coordinate of B. The great thing about unit vector is now you identify the fact that you can superimpose the position vector AB, and you know that this position vector AB is parallel to F, which is the one that you're looking for. Once you have identified this, then you know that they share the same unit vector. They have to, because they're parallel in the same direction. So both of them have a unit vector, F as unit vector here, called EF, of length 1, and position vector AB as unit vector EAB, of length 1. Those two are the same vector. Therefore, as we apply the definition of unit vector, which is in general, unit vector is equal to any vector divided by its own magnitude. Let's apply this to both AB and F, and we have position vector AB divided by length of AB is equal to the force F divided by its own magnitude. Because once we have identified that those two vectors are parallel, we know right away that EAB is equal to EF. Hence, as we apply the formula and the definition of the vector, we're going to put this. And now we can solve for vector f. Vector f is going to be magnitude of f divided by magnitude of AB times AB vector. And I'm going to group those two together. Since we know the physical bar, we know everything about A, everything but B. Therefore, we know vector AB. Once we know vector AB, we know its magnitude. Therefore, now we have expressed f as its magnitude, which is unknown, times its direction. And now this direction is entirely known. So we have managed to reduce the total unknown, the force, which has two properties, magnitude and direction. So we need to figure out both. And having identified the fact that this force is parallel to a position vector, now we have reduced our problem to only one unknown. We know its direction. We now only have to figure out its magnitude. Okay, so we just won one of the properties of that force. Very, very useful. And this can be done in 3D, 4D, 5D, ND, and ED. Okay, so that's one of the applications of unit vector. And you're going to see this later on in statics.